Our next speaker, I'm sure the people here needs no introduction. Nick Scoville is a professor at Caltech who has literally been at the vanguard of studying star formation for decades, both theoretically and observationally, and both on very small scales and very large scales. He's worked on everything from nearby cores up through winds from galaxies in the intergalactic medium. So he'll give us an overview of just a small subset of the things he's thought about in the last
Thank you, Phil. So what I want to do is give actually a very casual, very relaxed talk. I'd like people to ask questions. So workshop, so please ask questions during the talk, including objectionable ones. I know how to stop them. So what I want to do is, from my sort of intuitive point of view, review the properties of molecular clouds and talk about their internal structure, the intuition, which I think that gives you to understanding star formation, and then the issue of GMCs. They have environmental connections in a galaxy. Obviously, their high rates of star formation, particularly high mass star formation, inspire alarms, but I will point out that I think GMCs exist throughout galactic disks. So why is it that in spiral arms you have a high rate of star formation? Then an issue, related issue, is the lifetime of GMCs or molecules in particular. And I think there the answer is a little surprising, although people seem to be coming around to this point of view, that in fact once you form a molecule, it lasts a very long time. Then measuring star formation, various techniques for that, correlation of star formation with GMC properties, mass and density. So the cloud densities and masses are determined in many ways. The most reliable, in my opinion, is using the virial theorem to measure the self-gravitating mass of a cloud, and then use that to infer what the mean density is and overall mass is. There are extinction measurements, which can be done, of course, in the visible or moving into the near-infrared decay band. K-band has roughly 1/10 the extinction of the visible, so you can probe much deeper depths in clouds. But as we'll see in a second, the typical properties of these clouds are such that the overall visual extinction for a typical GMC is roughly around 20 magnitudes visual. So that's getting up to a couple magnitudes even at K-band. You can also measure molecular column densities by measuring, for example, rare isotopes, 13CO, 12CO, or other molecules, maybe C18O, and then computing a molecular column density, and also measure the densities from excitation analysis of various lines. Now, all of these are fraught with a little bit of difficulty because often you're observing optically thick lines. The optically thick lines, because of the large velocity gradients in these clouds, you actually see through the cloud, because different velocities occur at different places along the line of sight. But nevertheless, the excitation is affected by optical depth, and I'll review that very quickly. And also the molecular column densities depend upon what optical depth you assume. For example, the common assumption is you observe 13CO at sort of 1/5 the intensity of 12CO. So the naive presumption would be that 13CO has 1/5 optical depth, but has the same excitation temperature as 12CO. That, in fact, I think is really not the case in general, because even the 12CO with its higher optical depth is thermalized as a result not just of collisions with H2, but also as a function due to its trapping of line photons. And this is a substantial effect at density 200. Density 200, mean density of molecular clouds, you would never see CO thermalize. So you actually require photon trapping to enhance the optical depths, thermalize the 12CO, but at the same time, 13CO, which maybe has 1/60th or 1/80th of the column density of 12CO, will have lower optical depth, therefore less photon trapping, and therefore lower excitation temperature. So you can't just compare the brightness, relative brightness of the two lines and infer the optical depth of 13CO. So star formation tracers, typically in the visible, of course, one uses H alpha, or moving into the mid-infrared fine structure lines. UV continuum is used at high redshift. Radio free can be used on nearby galaxies. And radio non-thermal, there's an empirical correlation between the non-thermal flux density, and the star formation rate is gathered from the infrared luminosity. People have, in the last 10 years, started to use star counts in nearby molecular clouds to measure the star formation rate. That is looking at YSOs, and then, of course, using the infrared luminosity, which measures the luminosity of stars embedded within the cloud, and hence young stars which are formed in the cloud. But there are various things to be cautious about there. So just to get a picture of what the clouds look like, this is probably old hat for everybody. This is the Orion molecular cloud, which in fact is two clouds. Orion A, the H2 region here, or M42 is down in the lower cloud, southern cloud, here in the infrared, and then the upper cloud, enormous extent to both of these clouds, stretching over roughly 10 degrees of the sky. And if you look in the optical, you only see a very small portion of the action. There's another H2 region up in here called NGC 2024, but in the optical, you see only a very small part of the picture. Of course, the places where a couple OB stars have formed. So I put north here up because in the succeeding diagrams, we're changing the orientation, so it's a little challenge for the people without too much coffee so far. Now everything's been tipped on its side. Here is the southern cloud and the northern cloud, I think. And then this is in 12CO and 13CO, a paper by Ripple et al. From 2012. I think it's based upon data from the UMass 14-meter telescope. Now, the reason why I'm showing this is to underscore how similar the intensity maps are for 12CO and 13CO. You see basically identical structure, only scaled down in brightness by roughly a factor of 4 or 5, as I said. A little bit finer structure in 13CO, but basically, essentially every detail here you can see over in here. Now, suppose it was the case that 13CO really had optical depth 1/4. That would be incredibly unbelievable if that same 1/4 optical depth was occurring over this entire molecular cloud. It's not, in fact, and a lot of the excitation is provided by photon trapping, which I'll describe in a second. Now, here is a beautiful map, which I just saw last week for the first time from Karma by John Carpenter and Ahara, and a large group of collaborators, something like 3,000 mosaic pointings made with the Karma array. And what I'm going to show you very quickly is a movie going in velocities from 4 up to about 12 or 13 kilometers per second. And the structure here is really remarkable, fine structure. And looking at this movie, I saw one thing for the first time, and let's see if you see it. This is data including only interferometry. So there's large-scale flux, which is resolved out. But the immediate impression I got looking at this movie was how you see a preponderance of linear structures. And I've never seen that before in molecular cloud maps. So that's something which I think theoreticians need to understand. I think the observational interpretation of this data is not yet complete. Are these structures tubes? Are they intersections of planes? Or are they illuminated surface areas of the molecular cloud? And I'm sure John and company will be figuring that out before it's published by one of you guys. But it's a really beautiful map. Okay, now moving down to smaller scale structure, just to wake up Paul Goldsmith in the second row. This is a paper by Goldsmith et al. Studying the Taurus molecular cloud. And on top of this grayscale image are superposed the positions of young stellar objects, which they use to estimate the star formation rate as a function of column density of gas. This is column density I believe deduced from 12 and 13CO. Now, what I'm about to show you is what I consider the most beautiful astronomical image I've ever seen in any area of astronomy. And Paul and company deserve credit for this. Oh, it pays to review your slides before you. Okay, well, this has some significance. So what they've done here is to plot the number of those young stellar objects as a function of column density of H2. And you see the distribution looks like this, large range of column densities. But then the fraction of the pixels in the map as a function of column density, you can see there are the preponderance of the pixels are actually at low column density, whereas the star formation is spread over essentially the higher column densities. Now, the most beautiful image in astronomy. So this is using 12CO velocities on the Taurus cloud. And I'm not quite sure how unfortunately, the legend has been cut off, but there are 3 different velocity planes, red, green, and blue. And green is at 5 to 7 kilometers per second, red at 7 to 9, and green at, I guess, lower. It's blocked out on my screen, too. A lot of what? You see a lot of linear structures. Yes, but well, you mean like this? Well, no. But also you see these filamentary sheets. Yeah. I think the mass scale of the filaments in the Orion cloud is entirely different than the mass scale here. I believe that the whole mass of this Taurus complex is of the order of 10 to the 4th solar masses. Is that correct, Paul? And the Orion GMC is about 2 times 10 to the 5th. Anything you want to say, Paul, about this? But it is beautiful. Yeah. Okay, so here is a summary from the old days when I used to do this of molecular cloud properties, and I really don't think they've changed very much. The GMCs have, there are roughly 3,000 GMCs in the galaxy. If that sounds like a large number, I actually have a paper with John Gooden where we actually measured the properties of 1,400 GMCs in the Northern Hemisphere. So they actually exist, and you can actually quantify them. Now, the total mass of H2 is a little bit debatable, but we've always said about 2 times 10 to the 9 solar masses. Most of that is in the inner galaxy. If you look at the number of H2 regions in the galaxy, it's roughly around 200 with luminosity greater than that of M42. So most of these GMCs do not have H2 regions, active OB star formation. The GMCs have a mass spectrum, m to the minus 1.6. The median mass, such that 50% of the GMC mass is above and 50% below, is about 2 times 10 to the 5th. That's about what Orion is. The diameter, about 40 parsecs. If you take this mass and diameter, the density is about 180 per cc, mean volume density of molecular hydrogen. It's not to say that the density is uniform within the cloud, but that's the mean density in the cloud. The surface density, taking this number times this number, is about 2 times 10 to the 22 per square centimeter, about 20 magnitudes, or visual K-band extinction, about 2 magnitudes. Now, one of the remarkable things about these GMCs is that CO and all the molecular lines have very large line widths, roughly 10 times the thermal velocities at the gas temperature of 10 to the 20 degrees Kelvin. The GMCs are self-gravitating. They are not confined by an external pressure. There is no medium which would exert a sufficiently large pressure to keep them constrained. How do you know they're self-gravitating? If you take the mass which is needed, say the virial mass needed to bind the cloud, measure the column densities, say from extinction or molecular cloud column densities, those masses end up roughly equivalent to within a factor of 2, and that's good enough for any astronomy I've ever done. Okay, so here is an empirical plot which looks at the CO luminosity. CO luminosity is just the integrated brightness over the line, integrated over the projected area of the cloud. That CO luminosity plotted in these ridiculous units versus the virial mass. Why ridiculous? Because I actually invented them, so I can take the blame. And you see that there's a almost linear correlation. Actually, it's like roughly 0.9 power law. And you ask yourself, why is it that this optically thick line emission can possibly measure the mass of the cloud? So are we posting the talks for this? Okay. So I put some notes in here, which you don't need to go through in detail, but just, if you ever teach a course on this, it could be helpful. You can actually show that the CO luminosity of a cloud, which, as I said, is defined this way. If you use the virial theorem to relate the line width and this surface area of the cloud, you end up with a proportionality that the luminosity is proportional to the temperature of the first power divided by the mean density, the 1/2 power, times the mass of the GMC. So there's some rationale that if these parameters are roughly constant, then there'll be this proportionality. Now, obviously, temperatures vary little. They don't vary very much. You have molecular clouds. The mean molecular cloud temperature is probably about 10 degrees Kelvin. Near H2 regions, you get up to maybe 20, 30 degrees Kelvin. Not huge variation. Obviously, in little core regions, much higher temperatures, but I'm talking about the mean temperature for a cloud. And then the densities don't really vary very much either, if you go back to the size line width relation. So the constant of proportionality here is about 4 solar masses per unit of luminosity. Okay, little tutorial, since this was supposed to be, I guess, teaching on molecular excitation. I can make it extremely simple. Some of you may already be aware of it, but I think some probably not. So here is, for example, the CO rotational ladder. The transition we've been observing 1 to 0, 2 to 1, so on up. The radiation can be excited by collisions with molecular hydrogen. How hot does the gas have to be? Well, this energy spacing is only 5 degrees Kelvin. So any low temperature gas is well matched to the level spacing of the CO levels until you get the very high J. Now, if you calculate the critical density, that is, what density do you need to start to appreciably excite these levels approaching thermal equilibrium with the gas, that critical density is usually defined as NH2, the colliding particle density greater than the A coefficient divided by sigma V, the rate constant for collisions. And the assumption that this will lead to excitation temperatures approaching the kinetic temperature when you get to that point. So that for CO, if you plug in these numbers, is about 3,000 per cc. A coefficient is given by that number. For HCN and CS, 10 to the 4th, 10 to the 5th per cc. So what have we left out? What we've left out is radiative transitions. And the hint would be, I've already said that these are optically thick transitions. So if you go to an optically thick, say 2-level analysis, then you have to replace the A coefficient by the effective A coefficient, which is A times the escape probability of spontaneously emitted photons. Very simple. And in the limit of these large shear velocity gradients in clouds, when you go to tau greater than 1, the escape probability is 1 over tau. So essentially, A becomes A over tau. Now remember that tau, of course, has a factor which is the matrix element in it, or the A coefficient. So in fact, the A coefficient cancels out now. And the critical density now is just given by A beta divided by sigma V. It's independent of the A coefficient. The critical density does depend upon the molecular abundance and on the H2 density. And you can show roughly analytically that T excitation varies as 1/3 power of those quantities as you approach thermal equilibrium. So it's important to remember, and I say this and emphasize it, because you still in the literature now see people saying that HCN has a higher critical density because of its higher A coefficient. The A coefficient has nothing to do with it. It has to do with the abundance of HCN and what the column density is through the region. Okay, so one thing I want to point out is 13CO, for example, versus 12CO. The lower intensity of 13CO is probably due to the fact that to some extent the excitation temperature is lower, not just that it has a lower optical depth. And that's about it. Okay, so in summary, the star-forming clouds, the typical properties are listed here. They have high internal velocities, which, as Jonathan has said, are probably supersonic turbulence. That turbulence has an effective turbulent pressure, roughly 100 times the thermal pressure, And in turn, that's about 100 times. Sorry, this pressure is about 100 times the 3,000 NT pressure of the external medium also. No questions? So your intuition tells you, here is this massive GMC, 2 times 10 to the 5th solar masses, high internal turbulent pressure. What can you do to affect the star formation rate in that GMC? It's got to be hard affecting it from the outside, because the outside medium has a pressure 1/100th of the internal pressure in the GMC. If you set off a supernova 30 parsecs away, it's probably not going to have much effect. That's the magnitude of what you're trying to overcome in terms of this turbulent pressure. I just made up that number, but my guess is it probably is. What? Wrong? I see Hal smiling. I said it would be a casual talk, so buyer be warned. Of course, you didn't pay anything for this talk. So. Okay, how long do these GMCs last? Some of you have heard this before, so just bear with me. Suppose you look at the overall surface distribution of molecular and atomic gas in galaxies. And here's a classic example, M51, a CO map showing the inner disk of M51, and then an H1 map made from the VLA with the contours here, the CO contours, and then the H1. And obviously, there's a huge dichotomy here. H1 is distributed in the outer disk of the galaxy, as it is in the Milky Way, and the CO, or molecular gas, concentrated in the inner disk. So if you actually quantitatively do this analysis, probably the mean H2 density in this region is 4 to 10 times that of the atomic hydrogen in the same region. So what does that tell you about the lifetime? You might say to yourself, it tells me nothing. But in fact, suppose you have a picture in which gas is cycled from atomic or ionic phase, diffuse phase, into molecular phase. And it's cycled as you orbit in the disk of the galaxy. You might naturally say, well, the atomic phase should probably be in the inner arm regions where the gas is less dense, and the molecular phase may be in the spiral arms where the gas is forming OP stars. But you can't have that if you want to conserve mass. Suppose you have a flux of material from atomic to molecular back to atomic as you orbit in the disk of the galaxy. You can't take a species which has only, say, 1/5 of the mass of the other species. That is the, sorry, you can't take a species which has 5 times as much mass and concentrate it just in the spiral arms. So the molecular gas is actually widely distributed in the disk of the galaxy, and the cycling time for a molecule is probably longer than the cycling time from one arm to another, which might be 10 to the 8th years or longer. So I'm not going to go through this, but this is simple equation of continuity. You can put in whatever you want for the typical time scale for an atom to remain an atom, or an ion to remain an atom, an ion. And that number is probably in excess of 50 million years. Because once you go back to a diffuse phase, it takes a long time to gather up material. And if you just do 1 over square root of g rho as a characteristic time scale, you'd end up with a number about like this. So the time scale for the H2 has to be sort of 4 times this time scale, at least 10 to the 8th years and probably longer. Now, one thing to emphasize is that this is the time scale for a molecule to remain a molecule. It's not necessarily the time scale for a molecular cloud to remain that same structure. So you can certainly have a picture in which you form massive complexes in spiral arms, and then those sort of fragment into smaller molecular clouds, maybe it's kind of like torus cloud in between the arms.
Nick, you showed us H1 and CO. How about
The ionized mass is much less even than H1. And I don't remember the number, but it's like 10 times less, I think. But good point. And the presumption in this continuity argument is that you don't form a significant fraction of the gas into stars in one orbit. Otherwise, you have to put in a term there. But that is demonstrably true.
What fraction of molecular gas is in GMCs?
Well, as I said, in our galaxy, you have this mass spectrum where the 50% is above and below 2 times 10 to the fifth. The M51 is not. Sharon, yeah, right. You're talking later, right? Okay. No, so this is one thing which is kind of buried in the literature, but it's in an old paper of mine from back in the late 80s. What other evidence is there for this radical view that these GMCs last a long time? Well, there's actually, it looks like there might be equipartition of cloud kinetic energy. So this is something you can only do on our galaxy. Measure the dispersion scale height in perpendicular to the disk as a function of cloud mass. So I think this was done from that sample of 1,400 clouds I said we measured in the northern hemisphere. And in fact, the dispersion in the z direction is reduced as you go to higher cloud mass, as you would expect for equipartition. So that equipartition requires that you have several GMC collisions in order to equilibrate the kinetic energy of the clouds. Now, I'm somebody who never put error bars on plots. So obviously, I started early with this habit. So unfortunately, I don't have the error bars, and there's no way I could reconstruct them at this point. So you just have to believe that there's some evidence of this. But for some reason, it's never been redone. It would be nice to have, as far as I know. Adam?
If you wanted to do some other analysis of your prediction of population's intra-cloud dispersion, higher for low mass.
You mean sigma v?
Essentially sigma v between clouds instead of in clouds.
Yeah.
That should map to the same mechanism you're showing.
Yeah, right. Yeah. Have you done that?
We haven't, but I think Sharon may have done it by the end of the week. I don't know.
You young guys are just phenomenal. I got to retire soon.
Actually, Nick, couldn't an alternative explanation for that be if you populate a lot of the small clouds by doing something like what you said earlier, where you just blow up a big cloud by feedback or something?
We're going to get to that in a second, but go ahead.
Well, I was just thinking, like, momentum conservation would give you a trend kind of similar to what you saw, where the small fragments get bigger cakes.
Yeah, under the presumption that all clouds have been, disrupted on a short time scale.
Yeah.
Right. But I think that's a little inconsistent with that spatial distribution.
I guess the question would be, if you do that.
Don't tell me you're going to say you don't believe in mass conservation.
I believe in mass conservation, but I think that, you can cycle these things into small versus big blobs.
Yeah, okay, right.
But I guess to be fair, the concern is if you shred a big GMC into very small blobs or cloudlets, how do you prevent those from being dissociated if they get small? If they get too small.
Well, I mean, the minimum you need is, of course, 1 magnitude, roughly, extinction. And that's way down from 20 magnitudes. So you can afford to fragment into 5 different pieces easily. But, it's a workshop, so we'll discuss it. So the issue I wanted to highlight here was, why do you have if GMCs exist everywhere, as I've been arguing, why do you have star formation for massive stars, preferentially in the spiral arms? And what I would argue for is something which is very obvious. In the spiral arms, you have orbit crowding. Therefore, the spatial density of clouds becomes higher, even if the clouds are conserved as you move along these orbits. The spatial density of clouds is increased factors of 4 or 5 within the spiral arm as a result of the deviation of the orbits from circular. So that will obviously enhance the rate of cloud collisions, because that depends upon the number density of clouds per unit volume squared. Also in the spiral arms, there's a high amount of shear. And so that will also promote cloud collisions. So I would argue, and I think I've written a paper about this years ago, but it would be really nice to see a detailed analysis nowadays with good data, much better than we had in the past, of whether you see a roughly quadratic increase in the rate of star formation in the spiral arms versus the inner arm regions. But my feeling is, and this is entirely intuition, is that some star formation occurs in a quiescent fashion with just clumps of gas within GMCs collapsing to form stars. But then most of the OB star formation, where you form a massive cluster in order to get a few stars which have high mass, most of the OB star formation is probably a result of these cloud collisions, where there's massive compression of a large amount of gas at one time. And John has argued for this, and I believe it too. Now here's what I consider a possible example of this, and I was thinking last night as I was trying to fall asleep. There's actually an observational test which could be done. Here are the two Orion GMCs. The curious thing is that one H2 region is here, OB star formation region, another one here. And if you look at this, it looks like there are actually two clouds which have passed by each other, perhaps impinging on some area where they interacted. And the thing that I realized is you could actually test this model by measuring the proper motions of stars associated with this cloud versus stars in this cloud, and presumably they should be separating if they've had a collision in the past. You can't do that with the radial velocities because you have near-far ambiguity. John's scratching his beard. That's dangerous. This is California. We don't think out here. We just enjoy life. Okay, measuring, how much time do I have now? 5 minutes? 5 minutes, yeah. Okay, so measuring star formation, as I said, there are the various optical techniques. They obviously suffer from obscuration. For example, in the nucleus of ARP-220, the visual extinction is roughly 2,000 magnitudes. Now, I don't care. Optical astronomers can sort of see a little bit of fluff on the outside of the galaxy. They're never going to see into the center of the galaxy under those circumstances. So you need to go into the infrared or radio. Radio free. There's a sub-millimeter recombination lens. It's something that I've been doing recently with ALMA with a bunch of people in this room. And it turns out to be viable, but really only viable for objects out to sort of 50 megaparsecs. Otherwise, they're too weak. But then radio non-thermal and YSO star counts. So let me deal with the YSO star counts, and then I'm going to spend the rest of the time on the infrared luminosity. So here it's been done by a number of authors, including Paul, Heiderman, Lada, Gutermuth. And here from the Lada 2010 reference is for a collection of nearby clouds ranging from very low mass clouds up to Orion A and B. The cloud mass density measured from extinction, A sub K, K band. This is the mass at extinctions greater than 1/10 of a magnitude at K band. Here is the mass determined from the column density of dust at K band extinctions 8 times greater. So obviously it's going to be less. And then the number of YSOs listed over here and the derived star formation rate. Now this all sort of sounds like this is going to be the most precise technique for measuring star formation. But I would argue it actually has a number of problems, which are YSOs are really not well defined. The way they derive the star formation rate is to say, order of magnitude, the YSOs have a mean mass of about 0.5 solar masses. There's no consideration, as far as I could see in the papers, for the evolution down to the main sequence, the amount of time you spend in different phases, where these YSOs are in that evolution, and how reliable these mass estimates are. The other problem is that in some of the lower mass clouds in the sample, the numbers of objects that you have are so small that there's a big statistical uncertainty. There are extinction corrections, particularly in the most massive clouds. And also completeness of the YSO counts. The major problem is that the YSOs are not really a defined quantity, but the completeness is also not very well defined or discussed. And that is, if you have these clouds at varying distances, your sensitivity to mass will be quite different in different clouds due to different distances and due to different total extinctions through the cloud. It's not to say that it's not meaningful, but it's, you know, it's not the most precise, not as precise as some people would like you to believe. So this is from the Latta 2012 paper. Plotted horizontally is the mass within, first of all, the open symbols are the mass within the low extinction boundary of the cloud. And then the solid symbols are the mass within the high extinction boundaries of the cloud, representing sort of high column density and by implication high volume density gas. And they argue that, in fact, the star formation rate counted by the number of YSOs, determined from the number of YSOs, is better correlated with the dense gas than with the less dense gas. But you know, the correlation, it's a little better, obviously, but not all that much better. Now, the other thing is that, you know, it kind of is necessary that the star formation rate is correlated with dense gas, because in order to form stars, you have to have some gas compress and become denser. So I don't think it's telling you anything particularly astute, but, you know, it's been argued a lot that you should measure a dense gas tracer in order to trace star formation, which in the extragalactic point of view becomes more difficult because you have to go to these high excitation lines like HCN, CS, and those are fainter, of course. Okay, so how do you determine, and this is something I had to actually remind myself of, how do you measure star formation rate from infrared luminosity? What are the assumptions behind it? Now, if you just wanted to, say, teach a course and show how the infrared luminosity is related to the star formation rate, you apply a little bit of stellar physics. You realize that for these O, B, and A stars, which are producing most of the young stellar population luminosity, they're burning by the CNO cycle. And for these stars, it turns out, quite amazingly, that about 13% of the initial mass of the star gets processed through the CNO cycle while they're on the main sequence. So you just multiply these numbers, and that gives you the output luminosity of the stellar population. It actually agrees very well with what you get if you go to a complicated sort of starburst code like starburst 99 and estimate the luminosity to mass ratio. And you end up with the numbers which are around 2 times 10 to the minus 10 times LIR. Now, what are the issues or caveats? One is you form some young stars. How long is their radiation absorbed by dust? This cluster of young stars will gradually migrate outside the cloud. And that time scale will be roughly 10 to the 7 years, probably. Because once you form the stars, they're no longer affected by hydrodynamic forces. And the cloud is, so the cloud can be gradually moved away from the stars. Or the stars may also vacate a path to the surface of the cloud. So that's one issue. How long do the stars actually stay in the GMC? So this is a calculation I did using, once again, starburst 99. I took an instantaneous cluster of 10 to the 6 solar masses of stars, so I sampled all stellar masses. And that's this red curve here, 0.1 to 100 solar masses using a Krupa IMF. And the typical number, 2 times 10 to the minus 10, is right here. And that basically is good as long as the stars stay within the cloud for roughly 10 million years. It's kind of cut off, but this is mega years. Now, the other caveat is most of the luminosity from these young stellar clusters is provided by the high mass stars. If you don't form enough stars, you won't have any high mass stars. So I did the same calculation where I only went up to, say, 50 solar masses, 25, 10, 5. And you can see how the star formation rate per unit infrared luminosity is actually reduced as you go to, as you truncate the IMF. That's intuitively very obvious, but you know, even in the Latta study, it's a little surprising, because if I go back to this plot, if you read this figure caption, They've put nearby galactic clouds on the same scale as extragalactic whole galaxies, and they increased the star formation rate in the whole galaxies because they found that there was a disagreement between the star formation rates determined from YSOs and the infrared emission from the local clouds. So, that disagreement was to be expected because these clouds don't have high mass stars forming within them. So just remember that if you apply this infrared to star formation rate relation, you need to only look at regions where there's high mass star formation in addition to low mass star formation. Otherwise, it's not good. You need a different calibration. Okay, so this is also, once again, very old work, but the function of virial masses of these clouds, the LIR for these clouds, you can see when you get above about 10 to the 5th solar masses, then there's a fairly linear correlation between infrared luminosity and total mass of the cloud. This mass determined from all the gas from CO. And the galactic average, take the infrared luminosity of the Milky Way divided by the total molecular gas, 2 times 10 to the 9, you end up with a galactic average about 4 in solar units. This number, as Jonathan said, implies a cycling time of about 10 to 9 years for gas to stars. So one whole issue which needs to be dealt with, and hopefully will be discussed at this meeting, is you need to have ongoing accretion to the Milky Way to make up for this gas which is getting absorbed in the stars, about 70% of which ends up in the stars permanently, doesn't get recycled on a Hubble time. So maybe 60% rather. So that accretion needs to be coming from the nearby extragalactic space. Used to be people looked at H1 high velocity clouds as the possible source. They don't seem to have enough mass and inflow rate. I think, in fact, if you look at the physics of what would be accreting gas, it shouldn't be neutral. It should probably be ionized and probably would be seen in H-alpha surveys. So I'm getting about to be shut off. Just to finish off Krumholtz and McKee, there's a paper by Wu et al., I hope will be discussed a little bit, where they measured HCN and Milky Way GMCs, found between the virial mass and the HCN cores versus the infrared luminosity for all these collection of objects, these points here, and have this correlation between the two when you go up to high mass. When you actually plot the infrared luminosity versus the log of the volume density determined from the HCN, you actually have an anti-correlation with what would be expected from the Krumholtz and McKee relation. And it's not really discussed much in this paper, so maybe there should be a little discussion. So just quickly to remind you what goes on in infrared radiation. You have a source of luminosity, optical and UV photons absorbed by dust, hot grains seeing into A sub V of 1, then those grains re-radiate secondary photons and heat the more external gas. So let me just quickly remind you what the infrared spectrum looks like. These are models which I produced where I changed the overall mass of dust covering up a single luminosity source. And as the mass of dust is increased, the peak shifts to longer wavelengths because the shorter wavelength radiation is absorbed by overlying optically thick dust. But then also on the long wavelength tail, the Rayleigh-Jeans emission kicks up, linearly proportional to mass, and that's the technique which we've recently been using on the extragalactic scale to measure masses of ISM and galaxies. And so I'm not going to, let me just see if I have anything. So one final thing. The disruption of GMCs by H2 regions. So these are just some numbers I did over the weekend. I hadn't had my martini before I did them, so I think they're actually accurate. The issue is, can a single O4 star do significant damage to a GMC? So just taking order of magnitude numbers, and I'm only going through this because a number of theoreticians have said, yes, of course, you form OB stars, and they disrupt and destroy molecular clouds. I think that's not the case. There's no molecular cloud in which There's a substantial mass of ionized gas. By substantial, I mean comparable with the mass of the GMC in the outside the molecular cloud. So observationally, I think it's not supported, but numerically, the recombination time at density 200 per cc is about 640 years for ionized gas. At 10 kilometers per second, these ions traveling, say, 20 parsecs, it takes them 2 million years to get outside the cloud. So this is 3,000 recombination timescales. So basically, in order to maintain the ionization of each particle you're going to take from the inside of the cloud to the outside requires 3,000 Lyman continuum photons. So you can take one O4 star, produces 5 times 10 to the 49 Lyman continuum photons per second. Its age is roughly 3 million years. You get 4 times 10 to the 63 Lyman continuum photons. If you take the total mass of the cloud, divide up into H atoms, you require 7 times 10 to the 65, roughly 100 times more photons. So 100 O4 stars, O4 is like Theta 1c in Orion, would be capable of destroying the Orion molecular cloud if they were placed strategically in the cloud. But I think it's highly unlikely that you can form that many stars in the Orion cloud. It takes a large mass of star formation to actually occur. How much stellar mass is needed to form a single O4 star? It's a calculation I also did over the weekend. Total stellar mass of stars which have formed as maximum mass that you probe up on the top of the main sequence. And this has probably been done before, but I've never actually seen it. So, for example, if you form 100 solar masses of stars, the maximum mass you probe is about 10 solar masses in terms of stellar mass. In order to get an O4 star, which is about 50 solar masses, you require roughly 1,000 solar masses of stars actually forming, which is comparable with the Orion cluster. So I think I'll leave it at that and stop. Thank you.